Hey friends, welcome. Today we are going to discuss the Gibbs Adsorption Isotherm. Basically, this is a topic from the surface chemistry, and there are few more topics like Fluid Adsorption Isotherm. Then we have Langmuir Adsorption Isotherm. Those are very basic things. The Gibbs Adsorption Isotherm, it was given by very famous American mathematical physicist, that is J.W. Gibbs, and basically this adsorption isotherm was given for adsorption from the solutions. Now in case of a solution, we know that the concentration of the solute at the surface, so suppose this is our solution, so the concentration of the solute molecules at the surface of the solution is generally different from that in the bulk. So there is a difference, or there is a marked difference between the amount of solute molecules which are present in the bulk and which are present on the surface of the molecule. And if the surface tension of the solute is lower than that of the liquid, then the solute molecule, they tend to accumulate on the surface of the liquid and thereby decreasing its surface tension. And a qualitative treatment of the thermodynamics of adsorption of the solute at the surface of the liquid was given by Gibbs adsorption isotherm. We are going to see the qualitative treatment, that what will be the effect of the adsorbed molecule on the surface of any particular liquid. Now, in order to start the derivation, we will consider a system consisting of two components. So suppose if we consider that a system which is made up of N1 and N2, they are the number of moles of the two components, and similarly mu1 and mu2 are the chemical potentials of those components respectively. So the Gibbs free energy, that is G, as we know, it is given by mu1 n1 plus mu2 n2. So this will give us the free energy. Now as we are considering the adsorption on the surface, as a result we have to consider the change, or it will change the surface free energy, and we have to consider the surface energy also. So suppose if we consider that gamma is the surface energy which is equal or which is numerically same as the surface tension, and sigma is the surface area, or sigma is the surface area of the upper layer or of the surface, then the total amount or the total change in the Gibbs free energy will be this much amount. So we have to add this much, that is surface energy into the surface area, we have to add in this equation, and hence our free energy will become mu1 n1 plus mu2 n2 plus gamma into sigma. So this is our free energy. Now we will differentiate this equation. So when we differentiate this equation, this will be differentiation, or the differentiation will be done by differentiation by parts, and so the change in the free energy, that is dG, will be equal to, we can write it as mu1 dN1 plus N1 dmu1 plus N2 dmu2 plus mu2 dN2 plus gamma d sigma plus sigma d gamma. So this is the change in the free energy. Now when we look at this expression, then we may see that free energy, it is dependent on 5 independent variables, that are temperature, pressure, then mole fraction or number of moles of the first component N2, and the free surface or surface area. So these are the 5 variables on which our free energy is dependent, because if we change the temperature also, the surface area or the amount of surface or the number of molecules on the surface will change. If we change the pressure also, it will change. Number of moles, it will change, then it will also change. If we will change the container, obviously surface area will change, and hence the free energy will also change. So this free energy, it is dependent on these 5 parameters, and hence we can write free energy G is the function of temperature, pressure, N1, N2 and the surface area. We will differentiate this expression. So dg, we will differentiate this function with respect to one function keeping other functions constant. So I can write dg is equal to dg by dt, all the other p, n1, n2 and sigma are constant, into dt, plus similarly we will have dg by dt into, this will be dp, so into dp, other functions are constant, that is t, n1, n2, sigma, plus similarly dg by dn1 into dn1, similarly we will have dg by dn2 and plus we will have dg by d sigma into d sigma. So this will be the differentiation parts. And from thermodynamics we know that this partial derivatives have their respective thermodynamic function, that is rate of change of free energy with respect to temperature. It is nothing but this is equal to minus s. Similarly, change in free energy with respect to pressure, that is nothing but it is equal to volume. Again we know that change in free energy with respect to the number of moles, it is nothing but it is equal to chemical potential mu. This is also equal to chemical potential mu, and similarly, so this will be equal to mu1 and this will be equal to mu2. And similarly, change in free energy with respect to the surface area, it is nothing but it is the surface energy which is equal to the surface tension, and hence I can write this equal to gamma. So we will respectively substitute the individual thermodynamic parameters, and hence I can write dg is equal to this, I will have minus dt plus v into dp plus mu1 into dn1 plus mu2 into dn2 plus gamma into d sigma. So these are the terms. And again, suppose if we consider that our system is at constant temperature and constant pressure, then under such circumstances dt will be equal to 0 and dp will be equal to 0. That is, our system is at constant temperature and constant pressure, so both these terms will be 0, and hence both these terms will disappear from our expression, and hence the change in the free energy, that is dg, I can write it as mu1 dn1 plus mu2 dn2 plus gamma d sigma. So this is the expression. Now further, when we compare this expression and this expression, suppose this is our expression number 1 and this is our expression number 2. So further, when we compare expression number 1 and expression number 2, both are equal to dg, so both can be equated to each other, and the common terms, that is mu1 dn1, mu2 dn2 and gamma d sigma, that is mu1 dn1, mu2 dn2 and gamma d sigma. So these three terms are same, and hence we can directly cancel out these three terms, so the remaining terms will be equal to 0, and hence I can write n1 d mu1 plus n2 d mu2 plus sigma d gamma, that is equal to 0. Okay, further we can divide our system into two parts, that is consisting of all that portion which is under the influence of the surface force, that is surface phase. So we are having our system, and our system, we can, as we have discussed earlier, that the forces at the surface or the number of solute molecules at the surface are different from the number of molecules which are present in the bulk of the solution. So we can generally divide our solution in two parts. First, which are under the influence of the surface force, that is called the surface phase, and the remaining are the bulk of the solution. Okay, so we can divide our solution into two parts. One is our surface and other is the bulk of the solution. So suppose if we consider that N10 and N20 are the amount of the liquids and the solute which are present in the bulk phase. So this expression that we have obtained is the expression for the energy or expression for the molecules which are present on the surface. Okay, because sigma d gamma is nothing but it is related to surface, and so this expression is for our surface layer. And now we are calculating the expression which we will be getting in case of the bulk phase. And for the expression, or similarly for the expression in the bulk phase, we can write N10 and N20 are the number of moles of the two components in the bulk phase. That is, N10 will be our liquid and N20 will be our solute. Okay, in the bulk phase, then we can write that N10 d1 mu1 plus N20 d2 mu2, that is equal to 0. Okay, so we can write this expression. And further, since we know that the system is always, or our system is under equilibrium, then the chemical potential, or whenever the system is under equilibrium, we know that the chemical potential of the component in the bulk and in the phase or in the surface, it must be same. And once the system is being disturbed, it will again attain a new equilibrium, so that the change in the chemical potential must be identical to these two terms only. Okay, so hence, as the system is always under equilibrium, the chemical potential of all the constituents in the bulk as well as on the surface will be same. And if we disturb the equilibrium, then also new equilibrium will be generated, or new equilibrium will be attained, wherein again the chemical potential of both the components in the bulk as well as phase will be same. So hence we can rearrange this expression in the form of d mu1. So our expression will be, we will eliminate d mu1 from this expression. So we will have d mu1 will be equal to this, I can take it on right hand side, so it will be minus N20 d mu2 upon N10. And this value of d mu1 I can substitute in this expression. So when we substitute the value of d mu1 in this expression, we will have N1 into minus of N20 upon N10 into d mu2 plus N2 into d mu2 plus sigma d gamma, and that is equal to 0. So we will have this particular expression. We can take d mu2 common out from both these terms, and hence we will have N2 minus N1 N20 upon, I can write N10 into d mu2 plus sigma d gamma, and that is equal to 0. And further, when we rearrange, or we can rearrange this expression in the form of d gamma by d mu2, that is differential terms we will take on one side. So this I can take on right hand side, so that will be minus in sign, and then sigma I can take on division. So I will have minus of d gamma upon d mu2, that is equal to N2 minus N1 N20 upon N10 upon sigma. Okay, this quantity, that is this expression, it may be regarded as the excess concentration of the solute per unit area. Okay, because over here N2 is the number of moles of one of the two components. Say suppose if we consider solute, then that is associated with N1 amount of, also N2 is our solute and N1 is our solvent, and so this term, that is N1 N20 upon N10 is the corresponding number of moles of N1 that is associated with the solvent in the bulk phase. So this is the amount of number of N1 which is present in the bulk phase. So N2 minus this, so N2 is the total number of moles of our second component, and this term will give us the number of moles of our solute in the bulk phase. So total minus number of solvents which is present in the bulk phase will give us the amount of molecule which is present in the surface. So N2 is the total number of molecules. Okay, total number of moles of molecules, and this term, that is N1 N20 upon N10, it gives the number of moles of our solvent in the bulk. So this difference will give us the number of moles of the molecules which are present in or on the surface, and that divided by surface area will give us the surface excess. So this term it gives the excess concentration of the solute molecules which are present per unit area or surface, or this is called the surface concentration of the solute per unit area of the interface, and this generally it is represented as capital gamma, or this I can write it as capital gamma 2, where capital gamma 2 is the surface excess of the solute. Okay, so this surface excess, it can be defined as it is the excess concentration of the solute per unit area of the surface, and hence this gamma 2 I can write it equal to minus d gamma upon d mu 2. So this is our surface excess, which tells us about the total or excess concentration of the solute on the interface. Okay, now further, the chemical potential which is related to activity, or we know the relation of chemical potential, that is mu2 is equal to mu20 plus RT ln A2, where mu20 is a constant, or we know it is standard chemical potential and it is a constant value, and A2 is the activity of the solute. So when we differentiate it, we will have d mu2 is equal to, this term will be 0, and plus we will have RT dln A2. So this value we can substitute in the above expression, and hence we will have capital gamma 2, that is surface excess, will be equal to minus d gamma upon RT d ln A2, and this we know that d ln A2 I can write it in the form of dA2 by A2. So d ln A2 I can write in the form of dA2 by A2, and hence I will have minus of A2 by RT into d gamma upon dA2. So this will be at constant temperature. Further, suppose if we are considering that our solution is a very dilute solution, then and under dilute condition we know that the solution behaves ideally, so the activity can be replaced by the concentration term, and hence the surface excess, that is gamma 2, will be minus C2 upon RT d gamma upon dC2 at constant temperature, and this expression we can generalize it by writing in the form of the surface excess gamma is equal to minus C upon RT d gamma upon dC at constant temperature. So this expression is our Gibbs adsorption isotherm, which relates the surface excess with the thermodynamic parameters. And when we look at this expression, okay, from this expression we have the change in the surface tension with respect to the concentration, and when this value is a positive value, that is d gamma by dC is a positive value, or yes, it is positive value, then the adsorption is a negative. It means that further addition of any solute, it increases the surface tension of solute. So this is, if this is a positive value, then the net expression will always be, or the net value will be a negative value. That means that suppose if we are increasing the concentration of any solute, then as a result the surface tension of the solution will also increase. That is, as the surface excess has a negative value, that means the amount of molecule on the surface is increasing and the value of the surface tension will also increase. And similarly, if d gamma by dC has a negative value, then if this is negative, so this will be positive, and the value of surface excess will be a positive value, and such a solute will lower the surface tension of the solution. So if the value of the surface excess is positive, then the solute will lower the surface tension of the solution, and if the surface excess has a negative value, then in that case the addition of solute will increase the surface tension of a particular solution. So hope the topic is clear. Thank you very much.